So we've been doing exponential growth, and we did quite a bit with that. We did that at our practice problems to kind of get an idea about how these population growth models work and how they might be useful and how you can put them into some type of context. However, the exponential growth model, one of its basic assumptions is that you have an unlimited environment. And as you guys already pointed out, that isn't realistic most of the time. And then I pointed out that it is realistic sometimes when you have a colonizing species, a new environment opens up or something like that. But most of the time you're right, we have a limited environment. And so many populations are going to grow more like a logistic growth model. So that's where we are today. And so as density increases, resources become limited, so there's not enough to go around. And then we have to worry about something called intra-specific competition. So if it's intra-specific, what does that mean?
It's within a species.
Within the same species, right? So if I brought in a pizza, locked the door, left y'all in here for a couple of days, you'd fight with each other over that pizza, right? That's intra-specific. However, if I brought a pizza in here and I brought in some pizza-eating wolves and then locked you in here with the pizza-eating wolves, that would become inter-specific. And then after the wolves ate the pizza, they probably wouldn't be pizza-eating wolves anymore, right? All right, so that's where we're headed. And so what we need to do is we need to add to our exponential growth formula that we had. And remember I told you we need to know that formula, and we're going to track it and see how we modify it. And so we need to add something accounting for intraspecific competition. That's what's going to happen. All right. And so with logistic growth, eventually what happens is the growth will stop. So R will become 0. However, that doesn't mean that you don't have births and deaths. So what does a growth rate of 0 actually mean?
Even births and deaths?
Yeah, that the number being added to the population is equal to the number that are being removed from the population. Right? So keep that in mind. That doesn't mean that the population is just stopped. It just means that you have a balance. And specifically, the way our formulas work, a balance between the birth rate and death rate. Okay? And so that's why on the bottom it says an equilibrium. And that equilibrium tends to be at what we call K, which stands for carrying capacity. And the carrying capacity is the number of individuals of a particular species that the environment will support. As we get further into the model, probably by towards the end of the day, we'll talk more about K, I think. It's something that is not a constant, right? When we're modeling this, that's something you have to keep in mind. So the carrying capacity for animals right now, this fall, we're in a bit of a drought. The only rain we've had is from the 2 hurricanes. If we hadn't had those, we would be in really, really bad drought. And compared to last fall, we actually had a fairly moist fall, if I remember correctly. I might get my falls messed up. In other words, we have environmental change, right? We have something's different every year that's affecting these organisms, and so the carrying capacity adjusts according to that, right? And so it's a moving target. We're not going to let it move so much in our models, of course, but you just need to kind of keep that in mind. So you would need to be adjusting and thinking about what the carrying capacity is at all times. All right. And so here's the formula we're supposed to already know. The exponential growth formula, which is an instantaneous change in the population size divided by an instantaneous change in time equals the growth rate times the population size. That is the formula before we did our magical calculus box to make it into the formulas that we can use to actually do our homework with. But that magical calculus doesn't help us as we move into the logistic growth model. And like I told you before, we're not going to actually do any math problems associated with it. We're just going to look at it. All right. And so at the bottom now, we have the logistic growth model. Okay.
Thank you.
And we've added to that the end of the formula there to account for intraspecific competition. And I'm going to have a slide coming up where I'm going to box one side and tell you what that means, and box the other side and tell you what that means. But I'm already kind of hopefully set you up for this. Specifically, it's going to be our carrying capacity minus our population size, and then divided by the population size. And then that's going to influence your exponential growth formula. It's going to put limits on the exponential growth formula, essentially, is what it's going to do. So let's don't talk any further about it just yet. Let's look at its basic graph. And so our basic graph for the exponential growth was J-shaped. And so we described the basic shape of the logistic growth model as S-shaped. All right. As you're looking at it, if you don't look at the top part, well, first of all, it has the same axis. This is the basic one, no calculus, no fancy stuff pinned on it. So it's just the population size and how it's changing through time. But if you look at this part of the graph, it looks similar to what we have with exponential growth, right? Population growth is starting out slow at first and then begins to accelerate. And it starts out slow at first because
There's not very many individuals.
yeah, we don't have very many individuals reproducing, so you got to build your population before you can kind of accelerate your growth rate. And then at some point, the population growth begins to slow down. And as it's approaching the carrying capacity, it continues to slow down until eventually the growth rate reaches 0 at carrying capacity. A couple of things to note that I've seen on past exams is for some reason people just will put carrying capacity maybe over here or even above the line, but the carrying capacity is actually a number, right? It is a number, an actual population size. And so it belongs here on the y-axis. This is a theoretical graph. We don't have any numbers on it. But if we did, whatever number this is on the y-axis, that's the carrying capacity. Right? That's where it belongs. So put it in its proper place. And then we're going to add something else to this graph a little bit later, which we'll get to. All right. So population starts out slow, accelerates, slows down, and eventually reaches 0. The next slide is just putting those two graphs together. So I told you we would make comparisons between the two types of population growth. And so this one is our exponential growth, and this one is our logistic growth. They have the formula written in a different way here. Don't worry about it. We'll stick with it the way we've got it. But I'd like the comparison between these two. So you got population versus time, accelerates and then continues to accelerate forever and never, 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 never. Growth rate never changes. Here, the growth rate is changing. That's the biggest difference. So the growth rate starts out slow, accelerates, slows down, reaches 0. Okay, so let's go back and look at the formula a little bit more closely. So here's our logistic growth formula at the top. I've already shown it to you once, so I know you've got it memorized already. There it is again for us. And it's defining the different pieces a little bit more clearly. So K is carrying capacity, and then the K minus N divided by K. Okay. That is the unutilized opportunity for population growth. Did I have it wrong on the other? No, I had it right. I just said it wrong. Okay. Makes sense. Coming back on Wednesday is weird. All right, so that's the unutilized opportunity for population growth. We will more specifically, most of the time, just refer to it as intra-specific competition, because that's what it's really representing. But here's trying to get you to think about it in a different way. And so if you don't have, if your population size, if your N is smaller than the carrying capacity, and then you have a good opportunity for population growth, right? There's not a lot of competition, you have excess resources. As you reach the carrying capacity and your N and your K become closer together, then you don't have as much potential for population growth. So that's what this particular slide is referring to. Okay. Any questions about that? Okay. So this is the first slide we looked at, where we had exponential growth formula at the top to remind you what it looks like. And now I'm going to put those boxes on. This is something that I often do on the exam. I ask you to put the boxes on and label the different parts of the equation, because I think it's important for you to understand that they're all derived from one another. Okay? They're not creating anything new. We're just modifying the exponential growth formula, and that's all we're really going to do for all of the models that we look at. All right? And so first off, the first part, the dn over dt equals rn. That is our exponential growth. That is the potential for the population to grow unchecked, essentially. And so if we only have, if this part of the formula over here becomes 0, then we're going to grow exponentially. Well, no, not if it becomes 0, because 0 would cancel it out. If we remove it, we'll just remove it. Just remove that part of the graph, then we grow exponentially, or formula. All right. The second part represents interest-specific competition. And that is what's going to put limits on our population growth. So that's what's going to cause us to have an S-shaped curve rather than a J-shaped curve. So this formula gives us a J-shaped curve. This thing in its entirety, this whole thing, is what gives you the S-shaped curve. So this represents exponential growth. This represents logistic growth. The whole formula represents logistic growth. And this represents interest-specific competition limits on our exponential growth. All right. Any questions about what the pieces of the equation mean? Okay. And so on this one, I actually did this a little bit just a minute ago, but what we want to do is think about what happens to the growth rate depending on the size of n compared to k. All right? Because that's what we're subtracting out of the carrying capacity. We're subtracting out the population size. And so if the population size is less than, do it in order, less than k, the Pac-Man's eating k. That's how I was taught it when I was in school. It was the 80s. So if n is less than k, then that means that we have room for population growth, right? You still have resources. You're not at you're below the carrying capacity. And so you can have room for more individuals, and so the population is generally growing. If n is greater than k, then you've got a problem. That means we're higher, the population size is higher than the carrying capacity. There's not enough resources for all of the individuals to share, and therefore your population growth rate is going to be negative. And then if n and k are equal, they're going to zero out each other and cause our growth rate to be 0. So before I leave this slide where we're kind of thinking about what happens to the growth rate as you change the population size, this is also setting up a situation in which we can expand upon our S-shaped curve. Okay? And so basically what the model is going to do is we're going to grow like an S-shaped curve, but the population, if it gets too high, you're going to go up above k. That's going to cause the population growth to be negative, and it's going to bring it back down to k. And then if you go below k, then you're going to have room for the population to grow, and so it's going to bring it back up to k. And so what we're going to add in a few minutes is what we are going to call lags to the equation. That's because animals aren't going to know what k is, right? And so generally a population is not going to grow smoothly like that, but rather what's generally going to happen is it'll grow, overshoot, and correct, right? And so this equation actually allows for that in this way, okay, in this way. So if you overshoot, it's going to bring you back down to k. If you're under, it's going to bring you up to k. Does that make sense so far? Okay. So instead of actually working a problem, we're just going to look at a data set. And so in this example, we have squirrels again. Apparently the textbook I used to use liked squirrels. And it says you have a population where you start out with 10 squirrels, and then they follow that squirrel population for the next, looks like 70 years. And what you see is the population growth rate starts out kind of slow at first, between 0 and 1. We've only added 1 to the population, right? So 11. That doesn't mean we just added 1 squirrel. It means that a couple died and we added 3 or something like that, right? It's always a balancing act. But overall, we only added 1 individual. And then when you get in here, this is where the population growth is growing the fastest. We go from 30 to 40 in 1 year. And then you begin to slow down as you're approaching carrying capacity. And because this is a mathematical model, it's hard to hit exactly 50. And I do know that in their textbook example, they're giving us fractions of squirrels, but you know, whatever. The point of the fractions is to show you that it's really hard to get to 50. All right, so that's what it would look like, and as you can guess, this is a lot harder to do mathematics on, other than if we want to do a spreadsheet or something like that. But one of the things I try to point out is we start out slow, accelerate, slow down, right? All right, so the point at which the population growth rate is maximal, that's known as the inflection point. The inflection point. And it's just the carrying capacity divided by 2 is kind of a rule of thumb. It doesn't necessarily exactly hit that in a natural population, but model-wise, that's where we would look. And so for the squirrel example, if our carrying capacity is 50, then we would expect our population growth to be at its maximum at 25. So half. I can see maybe I want to change this a little bit. Because k over 2 is kind of like I was telling you about k. It's an actual number, right? And so if this is the squirrel population, this would be 50, and k over 2 would be 25. And so it should also be on the axis. That's my point. I think I'm just adding it in that picture is probably why I did that, because it's not a part of the original picture. But if I was drawing this, this is where k over 2 would go, about halfway between 0 and k. And it is a legit number. Any questions about that? Inflection point's question you want, right? All right, you got a population size of 100, or a carrying capacity is 100. What is the inflection point? 50. Yeah. All right. So next, what we're going to do, because I have a preview of our next slides, is we're going to compare logistic growth theoretical models. In other words, where we straightened out the line and did that stuff with exponential growth. To each other. All right, so the first one is this slide. This was where we took the exponential growth formula and we changed it into a formula of a straight line by just adding 0. I know y'all studied this a lot over break, I'm sure. And that plus 0, if you remember, was the y-intercept, and so this one goes through the y-intercept at 0 and it gives you the line. And so you have your instantaneous change in population size over time, and then your population size down here, your y-intercept at 0, and the slope of this line is your r. Okay, that's what it was for exponential growth. And basically doing this allowed us to do more simple math. Rise over run, and finding the slope of this line is easy. We can find the r pretty easy. That's what we were doing in your homework assignment, essentially. It's easier to find the slope of a straight line than it is to find the slope of a J-shaped line. Right? That's what I told you when we did this originally. All right, if we do the same thing, if we look at the dn, the instantaneous change in population size over the instantaneous change in time by n, with logistic growth, we don't get a straight line. It's still easier to work with this than it is to work with an S-shaped. We're just not going to do it because it's not easy like it is to work with a straight line. Okay, so it's not that easy to do. Just easier than the S-shaped. Okay? But when it does this, you can see the pattern that we were talking about, because the curve of this line is r, just like the slope of this line is r. And so what you see is that r starts out low, somewhere around halfway to the carrying capacity. That's when r hits its maximum. And then as you reach the carrying capacity, r slows down until finally at k it's back to 0. So that's the same pattern we were looking at on the previous slide, just putting it in a graphical form. So r starts out slow, you don't have very many individuals, hits a peak, and then it comes back down. Okay? Now remember, for exponential growth, we assume that r stays constant forever. And so this line just goes up and up and up and up and up and up and up with the same slope forever. All right, any questions about that one? So what are some of the assumptions of the logistic growth model? That, of course, all populations will often violate. Some of these are going to be very similar to what we had for the exponential growth model. So we'll start out with the age distributions are stable. And so the number of pre-reproductive to reproductive to post-reproductive is relatively constant from one generation to the next. So we don't have to put that into our model, basically. It continues our trend of ignoring immigration and immigration, which is always something to keep in mind. It's probably not exactly balanced, but the models tend to assume that it is. All right, this one's a lot longer in terms of words, but basically it says you can't have time lags. And so we're going to have to add to our model to account for a time lag if we want to. And so the logistic growth model says you do this, and that's it, right? You grow, you know exactly where carrying capacity is, you flatten out at carrying capacity. You can't overshoot and you can't go below. That's what this is saying. So you can't have any lags in the standard model. You can't have any lags. All right. This one's hard too. You have a predetermined carrying capacity. So we know what the carrying capacity is. It doesn't change. Although it's not too hard to account for that in the model, just to change the carrying capacity number. How would I want to, if I wanted to apply this to a real life situation, how would I determine a carrying capacity? I would sample the population over time and take an average, right? If I've got a field healthy population, that would be a good way to estimate carrying capacity. Okay? Because this most of the time when you're working with a population, you're working with an established population, I guess is what I'm getting at, right? You're not working at an initial population unless you are studying colonization. So if I want to go out and study the deer population on the hunt club behind my house, that population is already established. It's not like I'm going to go out and add 2 deer, remove all the rest of the deer, add 2 deer, and then follow them to see what the carrying capacity is, right? That's what I'm trying to get at. All right. The relationship between population size and growth rate is linear. Now this one is harder to make our minds wrap around, but we're going to try. We're going to try, and we're not going to think about it overly hard, which I think is pretty easy for most of us. All right, what this last one is referring to is the graph in which we graphed for exponential growth. So going back to our first model, we graphed R, and R was just a straight line, and I said it was a straight line forever and ever and ever. This is the relationship it's referring to in this last line. So that's what it does in exponential growth. What it does in logistic growth is generally it has the curve that we saw on the last slide, but you can take it, and if you put it into the same parameters as you get the straight line straight across for exponential growth, you can force it into a straight line. It's the only time you can kind of do that. Okay. And so on this one, I'm trying to show it to you. And what we have here is our instantaneous change in population size over an instantaneous change in time over our population size here. And you do get a straight line when you do this. And so what you're trying to think of is number of individuals being added to the population, essentially. Makes most sense here, where you'd have 0, right? And so rather than worrying about the whole line as a whole, what I want us to do is kind of focus on this part right here, okay? And so if we focus right here, at carrying capacity, we would expect to be adding 0 individuals overall, on average, right? We're still reproducing, we're still having mortality, but we expect it to be balanced at 0. If we go below carrying capacity, so if we move this way, so that our N is less than K, then we would expect to be adding individuals to the population. And if we move this way, in other words, our N is now larger than K, then we would expect our growth rate to be negative because we would need to remove individuals from the population. Okay? And so if we just focus on this part of the graph, it makes sense. It's the number of individuals being added to the population. Okay, so this is number of individuals, this is K. We move this way, R is going to be positive, If we're here, R is going to be 0. If we're here, R is going to be negative. That's all it's really trying to show for our purposes. Go to grad school, you can learn more. All right. This one is just, I feel like this curve is easier to understand. You know, so this is the same graph we already looked at, in which the growth rate starts out slow, accelerates, and then declines. And then it's just overlaid the straight line across it. And what it is trying to do is to take this curve and force it into a straight line so that you could do easier mathematics on it, essentially. I don't expect you to understand all that per se, but I do expect that you can understand what's happening right here. Okay? Are we good with that? I knew that was going to happen. Got too many shirts? It's too early in the winter to have 2 long sleeve shirts on, but I was cold. And now I'm going to have a camper. All right. Woo. So the next slide is just making your comparison. And so this is the exponential growth form, in which it goes on forever and ever and ever and ever and ever and ever and never changes. And then this is the same graph, same axes, when you force R into a straight line to get your logistic growth. So nothing new there, just putting those two on the same slide for you to think about. Whew! I think we're through the worst of it. Any questions about any of that? All right. So, like I said, the formula as it is right now, which is the k minus n over k added to the exponential growth formula, is a smooth S-shaped line. But generally speaking, that's not what you're going to observe in real life, because like I said, animals don't know what their carrying capacity is. They're going to sense their carrying capacity by abundance of resources or lack thereof. And so it's more likely that you're going to have some type of time lag. And so now we've got just a general graph showing you what I mean by time lag. So they've overshot the carrying capacity. And then what the time lag is going to do is it's going to allow some time to kind of bounce around and find the carrying capacity before flattening out. Okay? And so adding the time lag doesn't change that eventually the population is going to reach the carrying capacity and sit there. It just allows it to have some flexibility as it's getting to that carrying capacity. All right? That's what's going to happen. We're going to talk about 2 time lags and add those to our formula. The first one we're going to talk about is the reaction time lag. This is the lag between environmental change and a change in the rate of population growth. The environmental change and the change in the rate of population growth. And so what this is talking about is you're going along, you're a happy little critter living in your environment, you're at carrying capacity. So we're not even worried about the first part of the graph, we're just sitting at carrying capacity, and then we have a drought. And what this is saying is, at first, the population size is going to be at the old carrying capacity, because essentially in this situation, what's happening to the carrying capacity? It's changed, it's become lower, right? And so at first, when the drought first starts, it's going to be at its old carrying capacity. And it's going to take a minute, well, probably more than a minute, but it's going to take a minute for them to figure it out. And so their population is going to crash a little, bounce back maybe over, and then do that little kind of wavy thing until it settles in at the new carrying capacity. And so it's not like, oh no, there's a drought, and they just line up the extra individuals and then they're at K, right? That's not what's happening. It takes time for them to adjust. Since this particular time lag is dealing with number of individuals in the population, and its effect on carrying capacity, we're going to add this time lag to the n over here. And what it's going to be is t, so time, minus however long it takes for it to adjust. Right? That's what that is. And so the t time minus the adjustment for the change in the environment. I said that. I was trying to make sure. It had 2 asterisks on it, so I wanted to make sure we covered it, but I said that already. We're good. All right. Any questions about a reaction time lag? So this one's the environment changes. How long does it take until the population adjusts to the new carrying capacity? That's what we're looking at on this one. All right, the next one is related to this. It still deals with environmental change, but it deals with the gestation, or how long it takes for individuals to have an offspring, essentially. And so for humans, our gestation is 9 months, right? So this one's called a reproductive time lag. We're going to abbreviate it as G, representing gestation. And it's a lag between the environmental change that took place, the drought or whatever it happens to be, and it's not necessarily, it says change in length of gestation or if it's equivalent. It's not really that you're changing the length of the gestation per se, although I guess it could be cut off, if it's a resource issue, it could be cut off early. In that if you don't have enough food, then you would lose the offspring, essentially. But it's taken into account that if you have a bunch of pregnant individuals, elephants being a great example, I don't remember what their gestation is, but it's way longer than ours. Then all of those pregnant females don't automatically become not pregnant, essentially. And so you've got a lag where we may adjust to the environmental change, that's this right here, but then suddenly you have a bunch of individuals being born into the population that you don't have resources for. All right. We're adding that time lag in basically the length of the reproductive cycle is what this is talking about, over to the exponential growth part of the formula, because reproduction is going to determine how fast your population can grow. Right? The exponential part is just your growth, but the angle of that growth depends on your R, right? And R is where we have the birth rate, essentially. And so that's why we're putting it on that side of the equation. And so this one is just dealing with how many individuals and how they react to the environmental change. This one is accounting for how long their gestation period is and how that's going to be affected by the environment. And we've got both of them built into this equation. Got the double asterisks on there too. All right, any questions about either one of these lags? Also notice we kind of talked about those lags. It's not like if you're working in a real life situation that you're going to do this every time, right? What I'm saying is we're already up here, and then the environment changes, so your K changes, and now you've got to adjust to it. And then your K changes back, and now you've got to adjust to it. And so the model is continuing to work past that initial S shape that we learn about in our model, right? Trying to get you to think past that, I guess. Because that's just how do you get to K. And then, like we said, most of the populations you're going to work with should be at K. All right? All right. What happens to a population if R is negative for a long period of time? The answer's at the top in large letters. Extinction. All right? And so we worry about that a lot now. We have a lot of populations that are in decline. We're monitoring them. We hope by monitoring them and calling attention to declining populations that maybe they will begin to, maybe we will take action that will help to increase their growth rates and stuff like that. You know, I follow all the bird stuff, including duck stuff here and there. Don't follow the duck stuff that closely. But usually the Ducks Unlimited, I think it was about a month ago now, they release their annual duck reports and they show which populations are increasing and which populations are decreasing. And every year, some are decreasing, you know, and so, and sometimes they'll mention how long that decreasing trend is taking place. And what they're trying to do is to call attention to their supporters and to people who are interested in duck populations that, hey, we might want to try to figure out what's happening with this species, right? Because if it stays R, or stays negative, and we don't do anything to correct it, then we could lose that species. All right. Same with the 3 billion bird loss. I don't know if y'all know about that, but since the 70s, we've lost 3 billion birds, or about 1 in 4 birds in North America. And some species are increasing. Hawks, for example, are increasing on the whole. Woodpeckers are increasing, yay! But a lot of species, especially like grassland birds and things like that, are decreasing, giving an overall loss of biodiversity. So that's why we're talking about this a little bit. It is related to our population models. And so we want to talk about 2 types of extinctions. The first type of extinction is a deterministic extinction. And this is where you have some type of major event that can account for the loss of diversity. In this case, I give you a dramatic example that many people are familiar with. I don't even think that has to be in parentheses, but let me at least. There we go. The asteroid that hit the Yucatan Peninsula that sent us into a climate change event that led to the extinction of the dinosaurs, except for a couple of groups that made it through, which we call birds, for the most part. That is one example of a deterministic extinction. That's a dramatic one. Some other deterministic extinctions that we can see in the fossil record include when Pangea broke up. That caused a lot of extinctions. You would have had a lot of geologic activity at that time period. And then some of the collisions where the continents moved back together that would completely destroy marine environments and lead to some large-scale extinctions and stuff like that. And so while most people are most familiar with the extinction of the dinosaurs, that's definitely not the only deterministic extinction in our fossil record. The other type of extinction is the one we typically are more concerned with recently, and that are accelerated extinctions. And those are extinctions that are occurring because of human influence. I listed a few things, probably could update my list, but I listed a few things here. Habitat destruction is a huge one. I saw a cartoon that's probably been around for a while, but there's a bear standing in the forest, and then the bear's still standing there and they're cutting down the forest, and then the bear's standing there and it's in a city, and then somebody was like, where'd that bear come from? And he's like, I was here the whole time, right? And so the point is we're changing their habitat and causing some conflict in the return there. Introduced species cause a lot of problems for native species if they become invasive, which I think we've talked about here before. So there's a difference between an introduced species or exotic species and invasive species. Not all of the species introduced cause problems. The ones that get out of hand do, like zebra mussels and things like that. Exploitative hunting and fishing, so that just means the over hunting and fishing. Fishing tends to get the most attention here because we do a lot of ocean fishing at large scale because people like to eat that type of stuff. I don't even have climate change on the list, but obviously that's also contributing. So on the next slide, I just have a graph showing you some extinctions through time, and it's showing you a couple of the big extinction rates. The Permian extinction is, I believe that was breaking up some continents of some sort. Here's the extinction of the dinosaurs right there, which is not even one of the biggest peaks on there, but just the most famous one around, because people are fascinated by dinosaurs. One of the points of this particular graph is it's hard to work with the fossil data at times because you can't often take fossils down to species, for example, so you have to work at higher levels of taxonomy, which you can do a little bit more reliably with fossils. And so depending on the level of taxonomy, you get some different looking graphs. You still get the extinction peaks, of course, that kind of thing. And so that's what that red line showing number of families is kind of referring to. So it kind of depends on our classification, how we classify different types of things. The other thing that I also want to point out in this particular graph is you've got these big peaks that represent our deterministic extinctions, and this one doesn't go into modern times where you see the rise, the human rise, the accelerated extinctions, but that there's always a rate of extinction. That's the other thing I want to point out. And so extinctions are a part of the process. It's not unusual to have extinctions, and then also new species coming forward in place of the ones that went extinct. What we're worried about currently is what? The rate of extinctions is what we're worried about, is being pretty high, because those are usually changed. So I don't know how much y'all have discussed this in your past classes, but following the dinosaurs, that was a deterministic extinction. You had an adaptive radiation of mammals, right? And so I guess my point is, after you have some type of massive extinction, you usually end up with a massive change in the type of biodiversity on the planet, right? And so I talked to my non-majors. We've changed our non-majors class so that it's human impacts on the environment now, so we can talk about some of these types of issues. And so when I'm talking to them, I'll say it's not really so much, will there still be life on the planet? That will happen. And whatever's left behind will have an adaptive radiation and will go on. It's a question of, do human population want to be there, right? When this happens, is what I kind of talked to them about a little bit.
I'm not sure how accurate it is, but there's a new Morgan Freeman documentary on Netflix that goes into detail about each major extinction event since the Cambrian period.
Yeah. It's kind of interesting. I'm not real knowledgeable about it. I go, oh, that's interesting, and then I move on. I'd rather look at currently flying around healthy, happy birds. I'm kind of the same about bird evolution. I know a little bit about it, and when I read about it, I'm like, oh, that's interesting, but I'd rather go bird watching just generally. So I'm not going to be your expert on any of it. All right. Let me look real quick. All right, yeah, let's go ahead and do these, and then we'll take a break. They're not too hard to understand. In fact, maybe we'll just do this slide and then take a break, and then I'll come back and do the graphs. So ultimately, what we're talking about with logistic growth is density, right? So we've defined density already. And so if the population becomes too dense, has too many individuals, then that's a problem. And we talked about some of those problems when we discussed density, such as spread of disease and starvation, things like that. And then you could also have a population that's not dense enough, and we talked about some of the factors that impact that, such as not being able to find a mate, being a big one. If you're a species that's becoming extinct and it's hard for you to find a mate, that just adds to your extinction problems. And so that's what this is kind of getting at. That's why we're using the term density here, but we're still relating it to the logistic growth model. And so first we have our density independent effects. And that are things that change our population size, but it's not caused by intraspecific competition, essentially. It's caused by some external factor. In other words, it's kind of like a deterministic extinction. It's something that happens that knocks the population back. And so I give you some dramatic examples. It does not have to be this dramatic, but I give you like tsunami, hurricanes, things like that. And they certainly do cause density independent effects. So if you were looking at trees in East Tennessee and North Carolina, they took a huge hit, right? So if you lost a lot of individuals, that would be a density independent effect. That was not because of the density of trees that happened, right? Something else caused it. The opposite of this is a density dependent effect. And so this is something that causes the population size to change because of interspecific interactions. And so that's where you get into those problems of things like disease and starvation. That's why they had the free flu clinic on campus. Because what are we doing right now? Well, we've increased the density in this classroom tremendously, right? We bring you all together into large groups. And that makes it easier for us to switch diseases between each other. And then it gets even grosser, right? Y'all will leave and we'll bring another group in here. And after y'all coughed and licked the tables, and when the next group comes in and licks the tables, they're more likely to catch a disease, right? That's what it's talking about, density dependent effect. So density independence outside of your control, density independent, it's not, it would be wrong to say it's inside your control per se, but it is a byproduct of the size of your population in relation to your carrying capacity, right? And then, yeah, I think I'm gonna have to have a break and drink some water before I explain some more graphs. These graphs are not hard though, they're pretty easy. Okay, so this